Hello, hi friends, welcome to my YouTube channel. Today in this video, I would like to give the overall view of the liquid fuel combustion in the gas turbine applications. Okay, so myself, Dr. Raju Murugan. So I would like to give the small introduction about myself here. Right now, I'm working as a lead aerothermal and validation engineer in a startup company, which is mainly focusing on combustion chamber development, combustion system development, control system for the burner systems, etc. Before joining this startup company, I was working in another startup company that is a very short duration from December 2021 to February 2022. So that is my short time duration. Before joining this company, I was a postdoctoral fellowship, institute postdoctoral fellowship at IIT Bombay, in the Department of Aerospace Engineering. So that is also a very short duration because of the some personal issues. Uh, so now I would like to give my educational background. I have completed my PhD in the Department of Mechanical and Aerospace Engineering, IIT Hyderabad, 2020. So before joining my PhD, I was a master student at Department of Aerospace Engineering in MIT, Madras Institute of Technology. That is one of the oldest institute offering aerospace engineering. So that's the first institute also which is introduced the aerospace engineering. I completed my BTech in private college. So my area of research or my specialization, my research interest I listed here: automation and sprays, biofuels, alternative fuels, gel propellant, advanced diagnostic techniques such as PAV, PDPA. PAV is nothing but particle image velocimetry. So in this presentation, in this video, I will give overall view of PAV also, as well as PDPA, phase Doppler particle analyzer. That is very important tool to measure the spray droplet diameter as well as velocity simultaneously. And chemiluminescence, laser induced fluorescence, high speed imaging. These are the like advanced diagnostic techniques. Apart from my apart from this, I am interested in computational fluid dynamics also, as well as liquid fuel soul stabilized combustion. So in this video, I would like to entirely on liquid fuel soul stabilized combustion related stuff. And these are my few other points, information about me. My publications right now, five, that is I need to update, and the conference and my contact details. If you have any queries related to this video as well as this content, please feel free to contact me. Let's start the session. So these are my post PhD experience. Here I would like to give some of the in-depth of my work. Especially now I'm working as a lead aerothermal validation engineer. That is a startup company, uh, SBS Technologies Private Limited. So these are the my key role: combustion and burner system testing and validation. Key role for mine. Okay. Then triangulation of the 1D flow network data. So based on the simple analytical formula, this tool will work. And then CFD and experimental data. Burner development for the different fuels: hydrogen, natural gas, LPG, and different liquid fuels. So here I would like to give mainly on the liquid fuel combustion. In upcoming videos, I would like to give a gaseous fuel combustion also. So these are the main uh, work or like key role for mine in this company. So these are the main projects. So development and determination of the operability margins of a 3D printed hydrogen burner. So I am the test lead for that project. Before that, I was into another startup company, Aerostroils Energy Private Limited. There I was also into the experimental, and I was performed the full stabilized LDI based combustion system. LDI is nothing but the lean direct injection. So that is very useful to reduce the emissions in the combustion. In the postdoctoral fellowship, the title of my thesis or like my project is secondary automation of the gel propellants, especially design and development of the experimental setup for the secondary automation of the gel propellant. So here onwards I will start my PhD work. So I would like to thank my supervisor, Dr. Pankaj Escole. So right now he is a professor in the Department of Mechanical and Aerospace Engineering, IIT Hyderabad. So here in this slide, you can see my core competence in my PhD work. Here you can see my numerical work. So this is the twin field atomizer. In upcoming slides, you can see in detail about this one. And standalone injector means with the help of only injector, we characterize the spray characteristics. Okay. Then numerical simulation. So this is the numerical simulation work and integration of the standalone injector into the full stabilized combustion system or burner system. Okay, this is the open flame burner system. Here you can see this is the burner used for my experiments. So these are the different spray characteristic. Just exit of the atomizer. So here first I would like to give the introduction about the atomization and what are the importance application of the atomization. Okay, so atomization is the process. It is one type of process in which bulk volume or liquid, bulk volume of liquid is converted or transforms into the many millions of droplets like are known as spray. So here we can see this is the spray formation region. Here we can see the liquid core. These are the main liquid core is further breaks into the very finer spray. Okay, I already mentioned here very finer droplet. The droplet diameter would say in the range of like 10 micron to around 50 micron or 60 micron for the better combustion. If you have the bigger droplet diameter, so we will not get the complete combustion, which leads to the emission formation or incomplete combustion or localized incomplete combustion. So in order to achieve the proper combustion, we need to efficiently atomize the liquid fuel. Here we can see liquid core. Further it's break into the bigger ligament. Further it's break into the primary breakups. That means like bigger droplets and a secondary breakup. Very smaller finer spray. So this is the atomization process. This is happening because of the many different parameter. First one is like air assist. So we need to create the shear force or like pressure force in order to convert the liquid into the spray. So in the upcoming slides I will explain in details. So the important parameter which affect the spray characteristics are geometrical parameter. So that means like a design of the atomizer or injector and operating conditions, fluid velocity, air velocity, like that, and pressure. So these are the coming under operating parameter. And another one is the thermophysical properties. We know each and every liquid having the different thermophysical properties such as density. Let's consider density of water is not equal to the density of diesel or petrol. So density also one of the main parameter which plays a important role in the spray characterization, followed by the viscosity, temperature and surface tension. These are the four key parameters which dictates the spray characteristics. Okay, so first I explained about the automation and process and what are the important parameters which affect the spray characteristics. Further, here I would like to give the different classification of the atomizer. Single fluid atomizer. Here only liquid will be used for the atomization purpose. Then another classification is twin fluid atomizer. Here two fluid. One is liquid, another one is gas, media or air. Okay. These are the two different. Based on this two media, this fluid, this atomizer called as a twin fluid atomizer. Further, the twin fluid atomizer also classified into internal mixing atomizer and external mixing atomizer. Internal mixing atomizer is nothing but both fluids mixing inside the injector, whereas in the external mixing atomizer both fluids such as liquid and gas mixes at exit of the injector. So this is the schematic representation of the single fluid atomizer. Here we can see only liquid will come. Based on the supply pressure of the liquid, it will atomize. Okay, here the spray will come. Okay, based on the pressure. Okay, then I would like to show the another example. I mean another type of injector such as internal mixing. Here we can see gas or air is coming, and this is the entire geometry of the injector. Okay, this is the gas and this is the liquid. So both will mix inside the injector itself. Here itself it will mix. Okay, and it will create the final spray outside the injector. So this is called the internal mixing atomizer. I already clearly mentioned that both liquid and gas will mix inside the injector itself. This is the external mixing injector. Here we can see both water and air mixes at outside of the injector. So based on the different applications, so injector will be selected. Okay. So here the main application of the atomizer or injector I listed here. Spray painting. So in most of the industries, this technique or technology is used for the spray painting and spray drying, agricultural spray for for the agriculture purpose to in the agriculture field, and spray cleaning and liquid fuel combustion. This is the main key parameter for this efficient combustion in the gas turbine application. So here in this video, I will be focusing on the liquid fuel combustion and direct delivery. These are the main key application of the spray. So this is the typical gas turbine combustion system. In the upcoming slide, I will give the detail about this one. So this is the gas turbine combustion system. Here we can see gas turbine combustion system. So these are the important components or parts of the gas turbine combustion system. So here I would like to give the flow direction first. So this is flow direction. It's from left to right. So this is the air inlet. Okay, air inlet. This is the fuel inlet. Okay. So for the combustion, we all know we need air as well as the fuel. So that's what the main two inlet of the system. One is air, another one is the fuel inlet. Okay. So here we can see the surlers. Okay, suller vein or suller, whatever we can call, and in center we can see the injector or atomizer. Okay, so these are the main important components of the burner system. Okay, then followed by the these are the additional system in the combustion system or combustion chamber for the. So this we can call as the secondary air inlets to dilute the hot gas in the primary from the primary combustion chamber, and tertiary air. Still further, we need to dilute the temperature of the hot gas, and these are the outlet to the turbine blades. Okay, here we can see. Okay, so here we need to achieve the certain temperature in order to get the proper thrust for the GT application. So here we should not get the over temperature than the indicated temperature of the T80. T80 is the very important parameter here. I would like to explain here. This is nothing but the turbine inlet temperature. So based on the material and design of the turbine, we should have the some range of temperature. So we need to achieve the temperature with this combustion system with less emissions. So that is the main objective of the this combustion chamber. This is flame tube and this is the tertiary air. So these are the different holes. Mainly technically this called as the lures. Okay, different rows of lures will be there. So this and all to split the air into two different regions. Okay, this is a liner, this is outer casing. So this is outer casing, this is the liner. So here we can see the burner Sullivan's injector, and this is the mixer and dilution zone. I already mentioned. This is the primary combustion chamber. Okay, so this is the typical gas turbine combustion system. If you have any doubt, please comment. And next, I will move to the spray and automation because I already explained that the main application here. Okay, so injector, this will injector or atomizer. This will create a very finer spray for the efficient combustion and complete combustion. Okay, so here I would like to explain the flow blurring twin fluid atomization concept. It is nothing but the twin fluid atomizer. I will explain here. So this is the schematic representation of the injector. Here we can see I would like to give some of the parameter here. D is nothing but the liquid diameter or injector orifice diameter. H is the gap between the liquid tube end and the orifice disc dump plate. Okay, so this is the D and H. So internal will be the airflow and outer side is the internal will be a liquid flow, outer side is the airflow. Here we can see. So based on this simple geometrical parameter such as D and H, so we used to define as the H by D ratio. Okay, this is the important geometrical parameter. Okay, if H by D ratio is very high, here we can see, right? This is H by D ratio is greater, okay, high, and here H by D ratio is very less. Okay, if H by D ratio is greater, so we will see entirely the external mixing atomization. Here we can see external mixing. Here we can see a liquid and air is coming outside of the injector and it will mix here, it will create a spray here. Okay, whereas in the other configuration, if H by D ratio is less than certain value called 0.25, we will have the internal mixing also. Here we can see in this image, we can see clearly both liquid and air is mixing inside the injector. So here we can say that primary atomization is taking place inside the injector, whereas here it's taking place at exit of the injector or outside of the injector. Okay, so this is the simple geometrical representation or schematic representation of the flow blurring twin field atomizer. Here I would like to give some of the abbreviations used in this presentation. Okay, ALR, add to liquid ratio by mass, and LFR, liquid fuel, liquid flow rate, AFR, air flow rate. Okay, so first this technique was introduced by the Genan Calvo. He was and other researchers said they consider only HBD ratio less than 0.25 to achieve the flow blurring atomization. But my experimental research give the another important parameter such as not only the HBD ratio but the operating parameter also plays a very important role to achieve the flow blurring configuration. In upcoming slide you can see how they consider this 0.25. If you calculate the area of the the liquid tube as well as the area of the fuel air enter, so we can get this formula. Okay, that's it. So 5 cancel, dd cancel, h is nothing but 0.25d. Okay, that's what they derived this formula. But this is not hold. So for my experiments, from my experiments for higher HBD ratio also we observed the flow blurring atomization. So that is my uh, great innovative or identification for this research. So people are suggesting less than 0.25, but that is not good hold for all the categories, all the like operating conditions. So during my experiments, I was achieved the flow blurring atomization at higher HBD ratio also. So this I already explained here. If HBD ratio is greater than 0.25, it's external mixing, already I explained here this one. And HBD ratio is less than 0.5, it is a flow blurring internal mixing atomization here. So this is the very important slide to understand the flow blurring atomization based on the geometrical parameter only. Okay, let's move to the another slide. If you have any doubts, please comment. This is the experimental setup as well as the experimental results using the transparent injector. In previous slide I was explained that internal mixing also a important parameter to dictate whether the injector is operating at flow blurring configuration or flow focusing configuration. So here we can see this is the video. You can see here I already explained air, liquid, so it's mixing inside the injector. Okay, you keep on watching this video. I will explain about further experimental setup and geometrical configuration of the injector. I was used 6 mm injector. 6 mm is nothing but the diameter is 6 mm. I kept h by d ratio 0.25, and these are the my geometrical dimensions of the injector. So this is the image of the corresponding injector. So this is the ultra zoomed visualization and high speed image of the internal mixing and spray. Okay, this is the numerical simulation work. Okay, this is the numerical simulation work. Here also we can see how beautifully it's mixing inside the injector. Here I would like to bring one important point. Up to now, I am the first person to numerically capture the flow blurring atomization. Okay, so this is the geometrical or injector configuration. Here I would like to explain about the experimental setup. So yeah, this is the first I will explain about the airflow path here, and a liquid flow path, and a diagnostic techniques, that means imaging technique. Okay, so here we have the compressed air. We are controlling through the ball valve. I mean, this is like for the just flow opening and closing purpose. Okay, in order to accurately send the required amount of airflow rate, I used the MFC. MFC is nothing but the mass flow controller. So it will accurately, precisely control the required airflow rate to the system. Okay, and followed by the, this is a liquid line, liquid tank, peristaltic pump. Similarly, here for the air, I used MFC, whereas in the liquid fuel, I used peristaltic pump, followed by the pulse dampener, and this is the injector representation and spray, and these are the some diagnostic part. Here light source and diffuser seat in order to get the proper imaging. This is the high speed camera. Okay, so these are the experimental setup for my simple spray studies. Okay, using transparent injector. This is a transparent injector. We can see internal mixing also, external mixing also. This is a spray. I already showed this video. Okay, here we can see, here for the, here this representation is nothing but the ALR ratio, air to liquid ratio by mass. Okay, so I started with ALR ratio of 0.1. Here we can see there is no oscillation, or it will be a very minimal oscillation in the liquid jet. Means we are supplying very less air. Okay, ALR, air to liquid. Okay, this is very less. Similarly, as increasing ALR ratio, we can see oscillation in the liquid jet. Further, it's breaking the liquid jet into the back breakup mode of liquid stream. Here we can see further it's breaking. Here we can see fine breakup is happening. Here also we can see further breakup, but liquid penetration is starting here. Okay. Still, as increasing the ALR ratio, we can see we are getting very fine spray at exit of the injector, as well as air also penetrating inside the injector. Okay, here also we can see. So this is like ALR of 1.25. Here we can see higher air penetration in the injector at higher ALR ratio. Here we can see clearly see, as increasing the ALR ratio, we can see air penetration also increasing inside the injector. That means we are getting finer spray at higher ALR ratio. So this also videos. Here we can see at different ALR ratio how fast and how fine the atomization is. Here we can see at higher ALR ratio, we are getting very finer spray compared to other two ALR ratio, 1.25 as well as 1.5. Here we can see the spray droplet also very finer. So in order to understand the, previously I was understanding the effect of operating parameter on the spray characteristic as well as the penetration, air penetration length in the liquid tube by changing only the operating parameter. But my curiosity is this: why they kept only 0.25? Why not at higher or higher h by d ratio? So in order to understand the geometrical parameter also, I I came up with this different h by d ratio concept. Here we can see h by d ratio 0.25, where we can see very finer gap, and this is 0.12, sorry, 13, and 0.21, and this is the ultra case, like 0.42. The same setup, the setup is same. Okay, same setup. Here we can see what we like achieved, what I achieved through the experimental. Okay, here we can see for the H by D ratio of 0.05, liquid flow rate is constant 3.225 grams per second of a liquid. So here we can see these are the external spray and these are the internal high speed imaging of the spray. Here we can see bubble started inside the liquid tube. Spray also finer. So in order to understand the spray quality, we took these images with the help of lasers. This technique called the mist-scattering technique. At a higher ALR ratio, we can see very finer spray droplet through the high mist-scattering intensity. So based on this one, we classified, we segregated the data, and we came up with this regime plot. Here we can clearly see that for the different H by D ratio and ALR ratio, how the regime is shifting from flow focusing to flow blurring. Here we can see at lower ALR ratio, we are achieving at zero point 0.5 ALR itself. Further, as increasing H by D ratio, example for this one, we are achieving at higher ALR ratio. Similarly, for the 0.42, we are achieving the flow blurring concept at higher ALR ratio. That's what I clearly mentioned that people are uh, mentioned that only 0.25 geometrical configuration, whereas during my experimental study and research I was achieved this for the higher geometrical parameter also. This clearly brings the new research innovation from my research. So for higher HBD ratio also we can get the flow blurring concept. Okay, so this is the very important regime plot. Okay, next, so flow focusing mode of atomization, and this is the flow blurring. So based on the mean scattering intensity, we understand that the effect of liquid flow rate based ALR ratio at different uh, operating condition we perform. So here this is the liquid flow rate, and this is the liquid flow rate, and this is the air flow rate. Here one simple concept is, as increasing the liquid flow rate, to achieve the same ALR ratio, we need to supply the higher amount of air. Okay, this is how the plot is. So here we can see, as increasing ALR ratio, intensity is increasing. Okay, intensity, mis-scattering intensity. Okay, here we can see mis-scattering intensity is increasing. Here we can see as increasing the liquid flow rate also, this when compared to this is also increasing intensity. Okay, so this is mis-scattering RMS images. So how spread of the images and bigger droplet we can see. At lower ALR ratio we can see the bigger droplet, whereas at higher ALR ratio we don't have the bigger spray. Next, these are the mis-scattering intensity profiles at different locations. So this will give the quantitative, semi-quantitative information about the spray quality at different actual location and the spread. Here we can see 20 mm. I mean, this is the injector. From the injector exit spray 20 mm, 30 mm, 40 mm. We take a profile from the mis-scattering intensity. We made this plot. Okay, for the different configuration with the fixed ALR ratio. Okay, this gives the intensity value, and based on this one we can understand that how the spray quality is increasing. Here at 40 will I will show the 40. So this is the 40. So it is around 75. Here we can see it's around 90. Where here we can see it's 100. Here it's more than 100. So at the same location, with increasing liquid fuel rate with the constant ALR ratio, we are having higher intensity for the higher liquid flow rate. So this is the PAV image. Here in this presentation, I am not giving any detailed description about the PAV. In upcoming videos, I will make the working principle of the PAV and what are the main importance of the PAV. So based on the mesh cutting images and the laser mesh cutting images, we calculated the velocity field for the different operating conditions. Here we can see this is the contour of the velocity. This is the velocity ranges from 0 to 100 meter per second. Here we can see ALR1 and 1.5 for the different liquid flow rate. Here this is the liquid flow rate, and here we can see as increasing this one velocity is increasing. So because of the increasing in the airflow rate to achieve the higher ALR ratio. Here we can see the velocity magnitude for the different ALR ratio. So always we can see higher velocity for the higher ALR ratio. Okay. Whereas for the higher liquid flow rate, we observe the magnitude also higher. So this is the center line velocity of the spray droplet at a different ALR conditions. Here in this slide, I would like to bring the numerical simulation of the flow blurring concept. I already mentioned that up to now, I am the only person who performed the numerical simulation for the flow blurring atomization. So, if you want more detail about this work, uh, please feel free to comment. I will give the my journal paper for your reference. So, I used ANSYS Fluent software for this numerical simulation using VOF method, volume of fluid method, coupled with the LES. So these are the mesh understanding purpose for the different mesh cones. So first we need to understanding the effect of grid on the penetration length of the air in the liquid tube. So this I was performed. I used very finer mesh in order to accurately capture the air penetration length in the liquid tube. So this is the experimental numerical evidence comparison, and this I already explained about numerical simulation. These are the VOF at a different actual location in the liquid tube. Here we can see for the first plane, yeah, this is the one, and this is the second plane, this is the one. So here we can see at particular location we have the bubble in the airline. So that means internal mixing is happening inside the liquid tube. So these are the my geometrical and operating configuration for this numerical simulation study. So diameter is 4 mm and gap is 1 mm, and to bring the SPD ratio of 0.25, liquid flow rate is 0.55 grams per second. I was performed with constant liquid flow rate to achieve the different ALR ratio by varying the airflow rate. So these are the some qualitative images for the spray studies. Here we can see how nicely it's capturing the experimental values, sorry, images, and these are the finer spray droplet as increasing the time. So I was using adaptive mesh refinement. That's what as increasing time we can see very finer droplet also with respect to the time. Next, I would like to bring the finer. I would like to bring the another set of experimental system that is called the PDPA setup, phase Doppler particle analyzer. Here we can see this is a simple representation of the. So this is the laser NDLC laser. So signal processing unit, two different wavelength of the laser we used for this purpose, 561, 531, and spray. These are the receiver. Receiver will receive the signal from the transmitter and it will collect the data. So it will give the droplet diameter and droplet velocity. So this is like already explained. This is the injector configuration. So I used 1.5 mm injector and 0.3 mm gap in order to achieve the efficient automation. So for different operating parameter, liquid flow rate, Reynolds number, and ALR, sorry, AFR and ALR, air flow rate and ALR ratio for the three different liquid flow rate. So these are the important plots. This is the SMD, shorter mean diameter for the different actual location. Here also we can see for the different operating parameter. Here we can see for the flow blurring, we can see it's like following that starting from it's reducing the spray droplet diameter axially, whereas in the flow focusing we are not able to see that kind of trends also here. So we achieved very finer atomization for the both cases. It's like here we can see maximum of 60 microns or 70 microns for the cases. So similarly, this is like a PDPA distribution, probability density function distribution at a different location. So this and all detailed informations. If you want, please let me know. I will share this publication details for further. So this is like very important, useful to understand the spray droplet diameter and velocity simultaneously. This technique is called the joint probability density function. So previously we used to see like only one parameter considering this one, and here we used to do both droplet diameter and velocity simultaneously at the different positions to understand how the distribution is. Here we can see this all at a z is equal to at z is equal to 30 mm. We have all only by unimodal distribution. Here we can see bimodal distribution. We can see two peak here. Okay, so this is unimodal distributions. Here we can see the bimodal. So that means like here we have the two different velocities for the same group of droplet diameters. Similarly, this is like non-dimensional parameters. We convert that into the non-dimensional parameters such as Reynolds number and Weber number that we plotted. So, in order to understand the thermophysical property of the fluids, we performed the experimental study on the kerosene blended with the vegetable oil 100 percentage, sorry, 10 percentage, 15 percentage like that, and we performed the basic physical quantity measurements, physical properties measurements, sorry, density and viscosity. So here we can see the geometry representation, and these are like ultra zooming imaging. Here we can see just a 5 mm injector, I mean at exit of the injector, we captured very closely to understand this one. This is just 5 mm. Think about the 5 mm, this is very smaller quantity, I mean like smaller in size. So we used ultra zooming high speed misscattering technique to capture this one to understanding the near field atomization mechanism. So here we can see clearly the spray morphology is entirely different for the different category. So here clearly we can see that as increasing ALR, the I mean the core breakup of the bigger droplet is reducing. But whereas for the vegetable oil, because of the higher density and viscosity, we can see length also it's higher. So similarly, we can see as increasing the percentage of vegetable oil blending also, we can see the increasing trend. So this is like a mean image, this is RMS image. Here we can see how the droplets and all it's changing with respect to the different vegetable oil blending as well as the 100% vegetable oil. These are the centerline velocity profiles I already explained, and this is the mean centerline velocity and corresponding position. So just what's the length of this maximum point we reported and maximum value of the velocity. So this is a centerline velocity and the position. So here we can see for all the cases, velocity also higher for the 100% vegetable, and as well as the position also higher because of the higher viscosity and the higher density. It's taking longer time and longer distance to create the final spray droplets. So same only with respect to the preheating of temperature. We performed the preheating of vegetable oils also to understanding the spray characterization. As increasing the preheating, we can bring down the spray droplet diameter similar to the kerosene. Here we can see these are the two plots for the preheating. So here we can clearly see that this is without preheating, this is with preheating. We can see the plot is moving, shifting towards the kerosene fuel. Okay, so in order to obtain the proper spray characteristic similar to the kerosene, we need to preheat the vegetable oil to reduce the viscosity and density to achieve the better atomization. Next, this is the final concept I would like to explain about the Soul stabilized liquid fuel burner. Yeah, so this is the CAD modeling of the burner. So I used the solid edge software to design this burner. Here we can see. I will explain here. This is like a fabricated or fabricated one. Here we have the three different air connections. This is one for atomizer. The second one, this is for the swirler, and this one is for the co-flow arrangement. Here we can see the swirler, and this is the injector. So this is the blue color is for the liquid fuel line. So this is the Sul number formula we used. I used for the design of the swirlers. Here we can see Sul number 1, Sul number 1.5, and Sul number 2. How the swirler is angle is varying and number of vanes also varied. So in order to get the proper flow. This is the experimental setup. Here we can see I already explained, right. We are using MFC to control the hair. So we are using, I used three different MFCs. One is for the atomizing air, swirling air, and co-flow air, and similar setup. Sorry, liquid fuel using the peristaltic pump. So same laser sheet diagnostic technique and CCT camera for the capturing the laser that miscutting image. This is the top view of the my suture placed burner, and this is the velocity field. Without having any liquid flow, we use the seeding particles to understanding the aerodynamic characteristic of the solars. So we perform three different solar Reynolds number, as you can see here. As increasing the Reynolds number, the strong recirculation was observed. Here there is no strong recirculation. We have the very strong recirculation at higher Reynolds number, and this is the corresponding plots. And this is the effect of Reynolds number, full Reynolds number on the spray spreading. This is like with the spray without having any solar. With the solar we can see our variation. This is like without solar, just ALR variation. Here we can see with the solar increasing the Reynolds number how it's varying. So these are the important conclusion. So Sul material, bulk mean velocity of solar flow leads to the increase in the tangential mass flow, which increasing the radial spread of the spray. The rotational flow structures interacts with the core spray, and any increase in tangential mass flux would associate with increasing the rotational speed. Sul bulk velocity increasing the spray, we can see here. And these are the few images with respect to the spray, and these are the final combustion. Here we can see as increasing the Reynolds number of the solar, we can see how efficiently it's reducing the height of the flame as well as the spray. Here we can see efficient combustion is happening. So these are the main key combustion parameter study with the open flow. In order to understand the efficient of the solar, we need to do with the closed environment without having any disturbance. So these are the velocity parameter. Okay. So these are the important conclusion. So I would like to go through the important conclusion. very fastly. So here multiple internal microjet, okay, explain superior flow bearing atomization process. So air penetration length increases number of bubbles as well as the increasing uh, in with respect to the increasing in the ALR ratio. In through the numerical simulation also I captured the flow bearing concept. Formations are in the numerical simulation also we observe several microjet formations. So here not only the H by D ratio and ALR also plays a main role from shifting flow focusing to the flow bearing atomization. The penetration depends on not only H by D ratio and ALR ratio also. And penetration length that determines the spray quality. I already explained through the video as well as the images. Here these are the different important parameter. Vegetable oil and increasing 100 percentage compared to the kerosene. It is we need to do the preheating to understand the viscosity and density, and then we can bring the spray quality very high by adding the preheat. And the spray cone angle and height spreading with respect to the solar bulk velocity. Flame height reduces with increasing the Reynolds number due to the enhanced droplet evaporation, stronger flow recirculation zone, which brings more amount of burnt products towards the burner exit. So thank you so much for watching this video. I am concluding here. In the next video, I would like to bring some other new concept to you. Thank you so much for watching this video. Bye.